won't work with 7-digit numbers. Actually, the 7-digit one will work. So as long as each fourth digit is not 0, 7 digits will come. So you can shortcut it. He has a script to it. Yeah, but what I'm saying is you don't need to take your hair. What is there other than
All right, it is time. Let's go ahead and get started. Are you guys doing okay with the homework assignment? 5 people turned it in already, and I checked all 5, and they're all correct. So I know it's doable. The most important part of this homework assignment is really to understand how memory is organized. Because that's the basic part. That's what I want you to understand. Because of that's the first thing you have to do in order to program in assembly, is to understand how memory is organized, how bytes are organized, how you store multi-byte integers into memory. So those are all the things, and that's why we have the homework assignment the way it is designed right now. It's not designed to torture anyone. I'm sorry that if anyone feels that it's a torture test. But it really was designed so that you have to really understand what is going on when you allocate memory, initialize memory, and also how to use the various addressing modes in order to get the homework assignment done. If anyone has, first let me ask you this question. For people who have successfully done it or think that, yeah, I think I know how to do it, did you watch the video again from last week and find it useful, or you just kind of figure it out anyway?
I rewatched it.
Yeah, because the second time you watch it, you probably pick up something that you did not pick up in the class, because your mind probably focused on certain things when I do it in class, maybe the commands in GDB and other stuff that is just distracting you. But when you watch it the second time, you can watch the actual content, the concept part that I'm actually trying to explain at the same time when I'm fuzzing around with GDB and the assembler and stuff like that.
You actually made me realize how much I actually missed in a class. So now I'm like, all my other professors should videotape their stuff.
Well, in a way, it is time consuming to watch it again, but in another way, it's actually good because it's a full reproduction of what went on during the class. Unless I said something wrong in the class, everything is actually should be okay. Yes.
I find the part of the fact that I can pause it at any time and take more precise notes.
Mm-hmm. Yep. Yep, but it is still time consuming. It still takes you time to watch it again. But the nice thing is, if you feel that a certain part you already got it down, not a problem, or I'm just explaining how to use VI and you're not interested, you can just skip it. You can just fast forward and skip that portion. So it's good and bad. For those of you who find the video clip useful and find it certain parts of it, or at least certain parts of it useful, what you can also do is to make your own bookmark and indicate at what time of which video a particular concept was explained. You don't have to keep it with you at all times, especially when you watch it and you understand the concept already. Then you don't have to keep the bookmarks. But initially, the bookmarks can be useful. The other thing you can do is during the class, when the class starts. So during the class, you can also kind of jot down some notes and say, okay, Tech started to talk about this really complicated thing 15 minutes from the beginning of the class. So that way you can index into the video very, very quickly, just like that, and say, okay, I know I can just skip all the way to 14 minutes into the video, and I'll be pretty close to when I start to talk about that really awful concept that is hard to understand. Okay, so those are little tips that you can use during this class. The exam is not going to be memorization based. In other words, it's open book, open notes. Whether it's online or not is a different story, but it's always open book and open notes. So you can bring anything that is either handwritten or printed ahead of time and help you in the exam. So there's nothing that I will test you like, can you remember how to do blah, 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 blah. It is all about, do you understand the concepts? Can you apply those techniques and the concepts during the exam? It's all about application and understanding. Okay? Which I think are the right type of questions to ask for a programming class. For a history class, it probably is a little bit different. Yep.
You're talking a little bit about how to convert a number in base 8 into binary number.
In base 8 into binary,
Yeah.
I would just use a calculator.
Yeah. But
Yeah.
just use a calculator, just try to show us. how
Yeah,
to do
the
it.
Windows calculator can do base conversion. Does anyone know whether it can convert between base 8 and base 2?
Yeah.
Yes.
You
Yes.
can do
Okay.
it, but
There you go.
I want to do it by hand.
If you want to do it by
Yeah,
hand,
yeah.
it's the same principle as base 16, except you only have 8 digits, 0 to 7.
Yeah.
Each one corresponds to a 3-bit combination. So 0 in octal is 000 in binary. 1 is 001, and you go all the way to, like, let's say 5. Okay, 5 in octal is 101 in binary. 6 is 110, and 7 is 111. So instead of, in hexadecimal, we have clumps of 4 bits. In octal, we have clumps of 3 bits. And that makes it less useful because, 3 plus 3 plus 3 is 9, which is not at a byte boundary. But when you use hexadecimal, 4 plus 4 is 8, and it is exactly at a byte boundary. And that's why in this class, in just about any type of low-level programming class, you will find that people use hexadecimal a lot, and octal not really so much. I mean, octal is, it's kind of rare. I mean, I don't really find people use octal numbers too much these days. Okay, any questions about the homework assignments? No questions, right? Well, then we can go back and continue to talk about, all the stuff that we have talked about so far. We talked about memory sections, dot text versus dot data, memory allocation, basically your dot int, dot byte, dot fill, dot ASCII, and so on. Labels, okay, very, very useful concepts. And also the current location, which is the single dot, which is always there. It is just implicitly always there. Are there any questions about section 4, which is, stuff that we talked about last time already? No particular questions? Okay. Moving on to section 5, we covered some of these topics already. We covered immediate operands. Immediate operands, as the name implies, the value of the operand is the expression that is right after the $sign. There's nothing really complicated to it. If you say $5, then the operand has a value of 5. Yep.
Does it have actual numeric value of 5?
It will be 5 specified in the width that is implied by the instruction. So when you say move L, then it will be 5 specified as a 32-bit integer. If you say move B, it will be 5 specified as an 8-bit quantity. Okay. We talked about register. Registers is the easiest type of operand that can appear both on the source side and also the destination side. We talked a little bit about how an immediate operand cannot be it cannot be a destination because it doesn't make any sense. It's a constant. You cannot move something into a constant. It does not make any sense. So an immediate operand can only serve as the first operand of instructions in this class because it can only serve as a source and it can never serve as a destination. A register can be both a source and a destination. And then we started to talk about direct addressing mode, which looks confusingly similar to an immediate operand. Okay, so let's go ahead and take a look at this slide and also at that slide so we can do a little bit of a comparison. This talks about direct addressing mode. So the question now is, what exactly does it do? Okay, let's think about this. What is the first operand? What is the mode of that? It's an immediate operand because it starts with a $sign. Now, if it is a $sign, it basically means the value of this operand is just as the expression specifies. In this case, the expression is simple. It simply specifies 0. So the value of the operand is 0 itself. Okay, there's nothing special going on here. The second operand does not have a $sign, and it should not, because I just mentioned how an immediate operand cannot be a destination. You cannot change a constant. So what exactly are we specifying here? What are we going to change in this instruction?
Put a 0 right there, memory.
Sorry?
Put a 0 right to the memory location.
Well, this 0 specifies a memory location. So the operand, the second operand is actually the location is actually location 0. So what you specify is an address, not the content. You're specifying an address, so we're copying constant 0 into the byte or bytes at location 0. Now this is ambiguous, okay? In other words, can someone tell me how many bytes are we actually copying? Remember, we can have move byte, move W, move word, and move L, which is move long. This one doesn't say anything. It doesn't say B, W, or L, and there's nothing that can be implied either, because I'm not saying %BL, which implies 8-bit, or %AX, which implies 16-bit, or %EAX, which implies 32-bit. Right here, there's no register. There's no implied width in this case. So what do you think is the default width when I have instructions like this? It's actually L. So this is implicitly a move L instruction. It will change location 0, location 1, location 2, and location 3 to all zeros in this case. Are we doing okay with this? Yep.
So when you say like .long and the value, does it allocate 4 bytes for that?
.int will allocate 4 bytes.
Okay, .long, what's that?
I don't know. Is there a .long? I know we talked about .int, and that's 4 bytes. I'm not sure about .long. Okay. All right. So that's this is our first memory addressing mode. In other words, we are specifying a location in memory instead of a constant or a register. And there will be many, many to follow. And let's take a look at the next one. Oh, digression and in this, we talked about this already, so we can skip this portion. Indirect addressing mode. Now this one is quite interesting too. Many RISC architectures do not implement the direct addressing mode. In other words, if you look into the ARM architecture, if you look into the Spark architecture, many of those architectures, which are all RISC architectures, do not have the direct addressing mode. In other words, there's no way for your program, for your instructions, to specify, oh, I want to write to location XYZ, and XYZ is static. It is a fixed location. There's no way to specify a location like that. Instead, they have this, what we call an indirect addressing mode. The indirect addressing mode should be fairly familiar to those of you who remember pointers in the C and C++ class. Because in this case, let me just look at this instruction here. I will tell you exactly what it does. And I think after that you will say, oh, so EAX is a, okay, I'll talk about what that is later on. This instruction specifies the first operand $0 is an immediate operand. In other words, I am copying the value 0 to some destination. And because this is a move B instruction, I know exactly how many bytes I'm copying. I'm copying exactly only 1 byte. The destination in this case is not a register destination. In other words, I am not changing EAX. EAX, whatever is in EAX, which is a 32-bit register, is now considered as an address. And I'm changing whatever is at that address. That 1 byte at that address is being zeroed out in this case. It's being reset to 0. Okay? Is that doing okay? So let me say that again. If I were to use more common terms that you use in your other classes, this is basically saying I am overwriting the byte pointed to by EAX to 0. Yep.
So that points, the pointer is pointing to, or the pointer, pointing to the 0 location of the EAX, right? Can you, is there like reindexing where you can slide that around?
Well, EAX is our pointer, and we are changing that location to 0. However, by looking at just this instruction, I have no idea which location is being changed, because it is whatever the value of EAX is at the time of the execution of this instruction that determines which location is being overwritten by 0. Yep.
So if one of the registers stored a memory address and then you used it as the source for like rel, would you be able to do that with this syntax?
Yes, you can, because it is a memory operand. In other words, you're actually accessing memory, and
Yeah.
you can use it as the first operand or the second operand.
Okay.
The I386 instruction set has one single restriction. You can only specify up to one memory operand for each instruction. So if you use a memory operand, it doesn't matter which one, but if you specify a memory operand for the first one, then the second one cannot be a memory operand, and vice versa. Okay, good question. All right. Well, that's what I claim, but can you trust me? The answer is no. The answer is obviously no. And I'm going to teach you, well, not teach you, but I'm going to show you, how I would study for a class like this, okay? So I just read my own notes here. It says blah, 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 it explains a certain concept. But how do you confirm that this is actually correct?
Mess around with it.
Mess around, exactly. So what you want to do is to write a simple program, nothing complicated, just write a very simple program so that you can test whether this is actually right or not. In the process of deriving that test program, you are helping yourself understand the concepts. Now, when you run the program in GDB, only two things can be the outcome. One, you confirm your understanding, which is great. Two, somehow the outcome is not what you expect, which is also great, because it just pointed out maybe you have a misunderstanding somewhere. You think the instruction is going to do one thing, it's actually doing something else, which is good because you want to identify all those misunderstandings on your own before you do the homework assignment or even answer any questions in the test. So it is very, very important that you try to find some time to just run some experiments. Read my notes here, and then you ask, okay, how can I confirm whether what tag set was right or wrong? That is very, very important in a class like this. So I would just go ahead and do it, and you just use a terminal to do this. Go to today's folder. All the programs that I'm going to write are very simple, so there's really no need for me to upload the file. If you watch the video again, you can actually get the source file with one single screenshot. So let's go to today's folder. But I want to keep a record of all the sample programs that I have talked about in the class, and that's why I'm saving it. I'll just call this indirect S, and I'll try to design a program that is as simple as possible. Okay, we have to do a .global start here, and then we'll do something like something that we're already familiar with, such as L1, and then we have a .int here, and we'll put a specific pattern here. Let's see, we'll just say feed dad, I'm hungry. That turns out to be a valid, hexadecimal number 2. All right, so here's my program, and I'm going to do something here so I can test the program. If you wanted to stop at the very first instruction, it won't do it. That's why I put a no op here, so that my actual useful instruction is the second instruction, and I can stop there. The first thing I would do is move $L1 into register EAX here. And then the second thing I will do is to move, I don't know. Let's try a move E here. We'll specify EAX to EL, something along that line. If you want it to be a little bit tricky, you can also just do a little bit of calculation with the immediate operand. And then that's the end of the program. This stuff here is really just the exit code. I'm not going to explain it at this point. It will be explained later on. but the last 3 lines are not really that important, because when I run this in GDB, I probably won't even finish the program, because that part is not the useful part. All right. So given this program, can anyone, well, I want you guys to think about this program and basically think what will be in register BL after the move B instruction. In other words, after I execute line 6, what is going to be in BL? Let's think about it. Let's start with line 5. Okay. What is line 5 doing? The first operand is what? It's an immediate operand, right? It starts with a $sign. So what is the actual value that the first operand is specifying?
The label L1.
The label L1 plus 1.
Plus 1.
Okay. But what exactly is L1? L1 is a label, which means it has to be defined to a certain integer value. In this case, L1 is defined to be
Port location of integer.
Is the address of the first byte of the .int construct on line 2. Okay? Now, in this class, you have to remember when we say the address of, it is always the address of a byte. In assembly language programming, there is no such thing as, oh, it's the address of that 4-byte integer. It's only, you should say, it is the address of the first byte of the 4-byte integer. Okay, are we doing okay so far? But which byte are we talking about? What is the bit pattern corresponding to that?
Second byte.
It's the second byte, which is the 0D. Because of little endian, okay, when we have little endian, that means the least significant byte, which is the AD, is stored at exactly label L1. The second least significant byte, which is 0D, is stored at location L1 plus 1. This is stored at L1 plus 2, and this is stored at L1 plus 3. Are we doing okay so far? This is somewhat a repetition of what we talked about last week, but it doesn't hurt to reinforce those concepts. So basically what I'm doing here is this is an address, and because this whole thing is an immediate operand, I'm not going to this location. I am just saying copy the address itself to EAX, so that EAX ends up with the address L1 plus 1. Okay, are we doing okay so far? That we are not copying content from memory, we're simply copying the address into register EAX. And someone is going to say, oh, I know that concept in C. So the $sign is ampersand, the address of in C and C++. The answer is no. The answer is no, because ampersand is a high-level construct. It means address of, which means you need to have the concept of a variable in order to use the ampersand concept. In assembly language programming, there's no such thing as a variable. So it really is not address of. What happens when you say $1 or $2? There's no such thing as the address of 1 or the address of 2. So don't look at the $sign as the address of operator, even though sometimes it seems to suggest that it is the same thing. Yep.
So without the immediate operator, are you copying the content?
That is correct. Without the $sign, it is going to copy these bytes as well as the byte right next to, right after these 3 bytes into register EAX. Very good. Then the next instruction, because EAX actually has the address of L1 plus 1, we're now doing the indirect. In other words, I'm treating EAX as a pointer, and I'm copying whatever EAX points to register BL. And that turns out to be 0D, because EAX points to 0D in this byte, in this .int after the first instruction, after line 3. Okay. So I'm predicting that after line 6, BL should end up with a byte of 0D in hexadecimal. Okay, so you should do the same when you try to do some simple experiments to understand the concept. Do the same thing. Write a very simple program, as simplistic as it gets, to try to confirm your understanding of the concept. Make a prediction, It doesn't help if people do not say, okay, let me think about this, and I think this program should do blah blah blah. If people are not doing that step and simply go into GDB and actually observe the result in GDB, it's not learning as much as doing the prediction first and then use GDB to confirm whether your understanding is correct or not. Okay. So we'll just save this. I'm saving the editor here, making sure that I save the file first, and then I'll go ahead and assemble and link the program and then use GDB to run the program. This is called indirect.o, indirect.s. Link it. And use GDB to run it. Use L to list the program. I cannot put a breakpoint on line 4 anyway, and it is useless because it's a no-op instruction. So I'll put a breakpoint on line 5, and then I'll single step through those 2 instructions. And before we go any further, we can just go ahead and say, okay, what exactly is L1? And it shows an address. Okay, it shows the address of 8048054. And remember, this address is not always going to be the same. Okay, sometimes it is this, sometimes it's something else. It depends on where the operating system thinks is a good place to put your program when you start to run the program. Okay, so we single step through this. Oh, okay, I haven't run the program yet. Run the program, single step, and then I want to look at the value of EAX. There are 2 ways to do it. You can say IR EAX, info register EAX, and guess what? We have exactly that address here, and this is L1, this is L1 plus 1. And that's why you see a 5.4 at the end of L1, and you see a 5.5 in register EAX after the first instruction. Is everything making sense so far? Okay. So the next instruction is the one that I really want to understand. Is it actually going to go to location 8048055 and copy that 1 byte at that location into EL? Well, before I go any further, maybe it's a good idea to use GDB to confirm the actual content at that address. Which command should we use in GDB to do this? X would work, okay? Print will work too, but X works, in this case. So we'll say X slash, we are printing in hexadecimal, and this is a byte. And then we can just specify that location. Okay, I'm just repeating the address here. Press the Enter key, and it shows me, oh, it is location L1 plus 1, and the content or the byte at that location, in fact, is 0D. So I have double confirmation about what is going to be copied. So and then the next step is to print register BL, just to make sure that BL does not start with that value to begin with. And then a single step, print the value of BL again. Ah, tech, you're wrong. 13 and versus 0D, they're not the same. How about that? The 13 is in decimal, and then when I force print to use hexadecimal, it prints exactly 0D. So I have just confirmed that my understanding of the indirect addressing mode is in fact correct. Are there any questions at this point about the indirect addressing mode? No questions? Nothing mysterious here. But remember, the syntax is very, very tricky, because if you put the parentheses in, it is indirect. If you miss the parentheses, it is a register operand. Yep.
So what if we only copy the location of L1 into EAX, right? They both have the same location. How is this work? How does this work?
How do you want to change the program again?
No, I mean we have move L, right? Move L1 plus 1.
Yes.
And
dollar
the other
L1
side,
plus
yeah,
1.
Exactly. So that means we copy the location, the memory location of L1 plus 1 into EAX, right?
The first operand is an immediate operand. So whatever L1 plus 1 is the value of the first operand.
So
it turns out to be an address.
Yeah, address, yeah, exactly. So we copy the address at L1 plus 1 to the EAX, right?
We copy the address L1 plus 1 to
What if we
EAX,
not-
not at L1 plus 1.
Okay. So what if we only copy the address of L1 to EAX? They both the same have the same address, right?
No. If you move L, okay. So I think what you're asking is, what if we have an instruction like this,
No, the dollar sign L1.
like this?
Yeah.
Then it will just be the first byte. This will be the address of the first byte of the .int. So it will be the address of the AD of this long,
So-
dot long here. I mean dot int.
All right.
Okay. Now, just looking at this program here, I can probably throw in a few variations just to make sure that we understand how the variations are different from each other. So I'll give you guys some suggestions here.
How about removing the parentheses? Remove the EAX, the parentheses. What exactly is that do?
Sorry?
The parentheses.
Removing the parentheses. If you remove these parentheses, the assembler will complain because now you're moving a 32-bit into an 8-bit, and that cannot work. So the assembler would actually catch that one, and it won't even generate an object file in that case. Question? Okay. So a few variations. One variation looks like this. Then one variation, whoopsie, looks like this. And we'll just do all the possible combinations, right? Okay. I'm going to comment out these variations just so that you know that these are just variations. You should understand what the variations actually mean. Okay. Even though they are not, some of these will not work. I mean, it will just fail. Yeah, one of these will simply fail. Which one do you think will crash the program? If you just refer to the line number, which one will crash in this case? Or very likely will crash. I cannot say guarantee will crash. Line 8 and line 7 will both crash. Because they're both trying to overwrite the location pointed to by EAX. But what's in EAX right now? Remember, this is supposed to substitute the first instruction. So EAX is uninitialized. And your program only has access to a certain range of memory addresses, because the operating system doesn't want your program to mess up the whole system. So it is restricting your program only to have access to certain parts. If your program tries to access locations that are outside of your range, it will give you a GPF, a general protection fault in Windows, or simply called a segmentation fault in Linux. Yep.
The parentheses, what's the difference between parentheses around the register and no parentheses exactly? I'm more confused.
Without the, okay, on line 5, the destination is the register itself. I'm changing a register in this case. When you look at line 7 or line 8, the destination is not changing the register, it's changing whatever the register is pointing at.
Okay.
We are treating the register as a pointer, and we're changing the memory location at that address.
So it's like another immediate value. It's similar to $sign L1 plus 1.
Well, we don't know what is changing because in EAX is not initialized at this point.
That's it.
Because we're assuming these 4 are options, right? I mean, you only pick one of these 4. Is that okay, or am I not answering the question?
It would be really helpful if you go through the different options and say exactly what they're trying to do.
Ah, okay. So this will copy basically 4 bytes from the second least significant byte of the .int to register EX. You can actually try, number 6 will work. Number 6 is not going to crash, so what you should do is to actually try it out, see what it does. And these 2 are variations of the first 2. The only difference is where we are storing the result, and these 2 will crash. because EAX is not initialized, and most likely EAX has a value of 0 or very low value, and so those locations you cannot change.
So it would be trying to put the address or the value of L1
This
into a
will
memory address.
copy the address
Yeah.
L1 plus 1 to the 4 bytes pointed to IEX.
And it would be valid if EAX had a valid address.
That
or
is correct.
pointed to a
If
valid
EAX
address.
points to a location where you can change, yes, then the instruction will not fail. It will just change those 4 locations to the address L1 plus 1.
Or the immediate value of L1 plus 1.
Yes.
Okay.
Now this one is the interesting one. This one will not crash because it won't even assemble. Why won't it assemble? It has something to do with what I said a little bit earlier in the class.
It's trying to copy contents to a address location.
Exactly. The first operand is a direct operand. It is a memory type operand. The second operand is an indirect operand. It is also a memory operand. You can only have up to 1 memory operand when you use the move instruction, or just about any instructions in the i386 instruction set. So the assembler will look at this and go, nope, can't do it. This combination is not allowed. So line 10 is not going to crash because the assembler won't even let you specify an instruction like that. Okay. Are we doing okay so far with this? Enough confusion already?
Confused why that last one wouldn't work. To me, it would say,
You mean 10?
yeah.
Line 10? It's a restriction of the instruction set itself. In other words, the i386 instruction set does not support 2 operands that are both memory operands. Because in this case, they're both memory operands. This is a direct operand, which means L1 plus 1 itself specifies the location where we are copying from. The second one is a memory operand because EAX specifies the address of where we are overwriting. So they're both memory operands, and the instruction set, you can only have up to 1 memory operand when you specify an instruction. Yep.
Would you be able to do, like, let's say line 10 actually did work, but would you be able to do the same thing with 2 instructions?
Yes, you can. You have to use 2 instructions if this is what you want to do. Then you have to use 2 instructions. Basically, you move L1 plus 1 to a register, and then you move the register to indirect EAX in that case. So you have to separate it into 2 instructions.
Okay.
Very good point.
Why would they make it do that? Is there some reason why you only have 1 memory?
It has to do with the internal pathways of the ALU, and also the 4 cycles of a processor. The 4 cycles of a processor is something that I have not talked about. The 4 cycles are, let's see here, fetch is the first one. It basically goes out and actually get the instruction, which is a bit pattern from memory. The second step is decode. In other words, a mechanism inside the processor will take a look at the bit pattern, which is for instruction, and decide what to do. The third one is to process, to actually go through the calculation. If you have an add instruction, it would add. If you have a subtract instruction, it will subtract. In this case, if you have a move instruction, there's no calculation. The fourth step is called store. So if you have 1 memory operand, that's where it will store the result. Okay? But because of the restriction of how a processor is designed, you can only either specify, incoming from a, you can only specify 1 of the operands from a memory location, but not both of them. So it's a design restriction, not a software thing. You just have to live with it.
For now.
Yep. Are we doing okay so far with this sample program? But this is what I would do, in this class to actually get a good understanding of the concepts. And there are some sample code here with some explanations. Basically the same thing that we have been talking about. Let's go ahead and mess up this program, just so that we know what is the error message you should be seeing. So instead of using this instruction, which is the correct one that I want to use to illustrate the concept, let's go ahead and uncomment this one. I said this is going to crash because EAX most likely has an invalid value. It is a location that you cannot change. But we want to do this kind of controlled experiment. Why do you think I want to do this? To waste the time? I mean, after all, you guys pay what, $36 per unit. This is a 4-unit class. That's a bit of money. Well, we're not doing this to waste money, because why do we want to do controlled experiments? We know exactly this program is going to crash, and we just want to see how it crashes. Why do we want to do that? So that next time when you see the same type of error message, you know how to interpret the error message. Okay? That is why we are going to do this.
To reassemble, you always have to exit GDB.
No, you don't have to. But GDB kind of locks into the executable. You can make GDB to reread the executable. That's okay too. But I just usually use one single shell for assembling, linking, and then GDB, and then another shell just to use the editor. I mean, that's entirely up to you. You can learn that command in GDB just to reload it. And I think it is just load. So help load. Dynamically load file into the running program and record its symbol for access from GDB. That may or may not be what you want.
File, I believe, actually.
File?
It's the word file.
Use file as program to be debugged. All right, yep, very good. It's rare that I have someone in the class who actually knows GDB. Do you use it extensively? A lot? All right. So we want to run the program because we know it's going to crash. So when it crashes, this is the error message it's giving you. Program receive signal sig segmentation fault sig v, and it says which location. It tells you which instruction is causing this problem. It tells you the instruction is on line 8. Now on line 8, there's only one part that is suspicious. The first operand cannot be suspicious, can it? The first operand is an immediate operand, so we should never have a problem with an immediate operand. So it has to be the second operand. So if you have a suspicion like that and say, well, maybe it's the second operand that's causing the problem, and the next thing you should do is to look at the register EAX. EAX has a value of 0. In other words, I was trying to overwrite location 0, 1, 2, and 3 with the address L1 + 1. Location 0 is not a part of the program space that you can overwrite. The operating system tells the processor, if this program ever tries to access locations outside of this small range of addresses, generate a segmentation fault so that I know about it. Okay, and that's what it is. Okay, the hardware is telling the operating system and say, hey, this program is trying to do something that is not nice. And then the operating system turns around to tell GDB about it, and then GDB tells you that your program is trying to access a location that you're not supposed to.
Tattletale.
Yep, tattletale. Yep. But tattletale is good in this case. It's also good that your program has its own address space to play with. It does not overlap with the address space of other programs. Well, not always true, but for the most part, it is true. Yep.
If you try to use the immediate operand to move a value that is larger than the, say, register you want to move it to, will it truncate or will it not assemble?
The assembler will complain. Either the assembler or the linker will complain. It depends on, I think the linker will complain in this case because the linker actually gets the last say of what is the actual value of a particular operand. So if you try to specify something that cannot be stored in an 8-bit register as an immediate operand, the linker will most likely complain about it. The assembler may complain about it if it is resolvable at assemble time. But if it is only resolvable at link time, then the linker will complain.
Will the program run?
I believe the linker will not even generate an executable in that case. So it won't truncate it. If you want to truncate it, if that's your intention to truncate it, you can actually do the truncation. When you do the calculation, you basically specify a bit mask, do an ampersand, which is bitwise and with FF. So you intentionally, in that case, truncate it to just the least significant 8 bits. And then in that case, I think it will be okay because the actual value can be stored in 8 bits.
All right.
Okay. All right. So let's move on to something that's, well, digression. This is a cisp versus RISC instruction set. We talked about this already last time. It has to do with, well, maybe not even last time. I think this is before our last meeting. A RISC processor core is less expensive to manufacture because it has fewer transistors. It doesn't need as many transistors. And you can also fit more RISC processors onto a single wafer, which means your yield is higher. The yield is basically saying, okay, on a wafer, which is typically about yay big, I think the old ones are 20 centimeters in terms of diameter, and I think the new ones are what, 30?
350 seems right. I don't know.
So they're 35 centimeters now, up to.
350 millimeters.
Okay, but if your die size is smaller, then you can make more per wafer. But not only that, but your defect rate will go down. Because if you have defects, and there's always defect somewhere on a wafer, but if the defect rate is always the same, think about it this way. Think about a processor that is so complicated it uses up the entire wafer. Okay, it's easy to think of extreme cases, right? And according to statistics, 99% of the time you will end up with at least 3 defects on a single wafer. Okay, so what is your yield in that case? Pretty darn close to 0. It'll be a very, 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 very lucky day that you have one single processor that has no defects. On the other hand, let's say you have a little die, you have a little RISC processor that is so tiny that out of the entire wafer, you can make 10,000 cores, okay? And, statistically speaking, 99% of the time you end up with 3 defects on the same wafer, okay? So what is the yield in this case?
Nearly 100%.
Nearly 100%, because it is basically 10,000 minus 3, the whole thing divided by 10,000. That's your yield. So that's why RISC processors are very economical, because the yield of making these processors is actually higher than an equivalent CISC processor. What about processing speed? A CISC core is actually slightly faster to a comparable RISC core when instructions are examined locally, and so on and so forth. In other words, if you look at one single instruction at a time, it is true that sometimes, because with a RISC processor, you have to execute several instructions to make up for one single instruction in the CISC processor. Okay, just the fact that you have to go out to memory several times to get the instructions make it a little bit slower. But you can also argue in some other cases and say that, well, but hold on a second here. Some of the RISC architectures can be effectively faster than the CISC architecture. There's one thing that helps a lot of the RISC architectures is the number of registers. Okay, a lot of the RISC architectures come with 16, 32 general purpose registers. Why would that be helpful? Remember what registers are? They are basically little post-its right next to my calculator. Pretend this is a calculator. Okay, so a CISC architecture spends all the transistors, all the silicon on decoding instructions and all those complicated stuff. So I can only end up with, let's say, 4 little post-its to store results from my calculations. Anything other than those 4, I have to go all the way back to the library to store something or to get something. When you use a RISC architecture, the core of the processor is so small that you have silicon left, so you can have, let's say, 32 registers. So now I have 32 little post-its around me, and I can store a lot of intermediate results from the calculations. Why would that be helpful?
Times of heavy processing.
I don't need to go back to the library as often, right? Because now I have 30.
Many calculations before having to go get one.
It depends on the structure of the program too, but in general, yes, I have more space to store intermediate results before I have to go all the way back to the library to store something or to fetch something. Okay? And that benefit mostly is only because of our compilers. Because the compiler can do optimization and say, okay, how are we going to utilize the registers the best so that we minimize the number of trips to the library. Okay? And RISC architectures are particularly useful for that because they usually have more registers. Yep.
Question, I guess as an aside, the 64-bit version of i386, AMD 64, got added 616 general purpose registers. Quite nice.
All right.
Just
Now, there may be one point here that, oh, this is actually also true. The last point here is the most interesting part. Okay. The data centers, in other words, the high processing power, data centers. When we talk about data centers, we're talking about, the rendering lab of Pixar and so on and so forth. They need to pack as much processing power as possible into a building. Okay. What do you think is the limiting factor? It's not rack space. It is actually power now. It's not really just power, it is also heat extraction. Okay, those two kind of go hand in hand. Okay, how many of you, I know some of you guys here, mod your PCs and try to get the most out of it. Was it this class that someone told me, I'm running my Q6600 stock and it's a waste of that particular core?
It was this class.
It was this class? Okay.
It's not here today.
Oh, okay, so the modder is not here. Okay, so, but what are we running up against when you try to overclock a processor? There are several things you're running up against, but one particular one is really obvious. Heat. Okay, how do you well, because when you overclock a processor, it will generate more heat than running it stock. So when you run it very hot, then you have to find a way to extract all that heat out of the processor quickly enough so the processor doesn't die, because of heat. And the data center has exactly the same problem. Okay.
They're packed so tight together.
And they're very tight. And so it ends up, this is a limiting factor of how much processing power you can pack inside a data center. It's also how much power can you feed into the building too. Does anyone know that Google actually has the license to become its own, is it generator or supplier of energy, supplier of electricity? In other words, they're all set up to run their own power plants.
For their data centers?
Hmm?
For their data centers?
Well, not only for their own data center, but I'm pretty sure that's a motivation why they are, getting a license to become a power plant, basically. Yep.
For what I've read about data centers, the main problem with cooling a big server rack isn't necessarily cooling the individual processor cores, but it's all the heat that dumps into the room that they're in. It's getting that heat out.
Yep.
So that's true?
Well, it's just a the net amount of heat that is generated because of all of these cores. If you look at the power consumption of a processor, let's say you have a modern processor, is it about 100 watts these days?
65 watts to 90.
65 watts? Okay, let's say 65 watts. How much of the 65 watts are wasted as heat and how much of that is actually done doing the calculations?
I want to say it's got to be really high.
Pretty small amount, actually.
Small amount actually being you doing the calculations, and most of the 65 watts are heat.
Yeah, most of it.
Okay, so that means the more powerful processors or more power-hungry processors you pack in the data center, the more difficult it is to extract all that heat out and make sure the room stays at a particular fixed temperature. And that turns out to be the limiting factor. And now, the holy grail of processor design used to be MIPS. Okay, we do all the calculations, all the comparison in MIPS, M-I-P-S, million instructions per second. Yes, modern processors can do giga instructions per second, but it's the same idea. How many instructions can you execute per second? That used to be the holy grail. They all do benchmarks comparing that. That is no longer the case. Now we want to see how many instructions you can execute per watt. Well, that's the wrong unit. Per joules. J for joules or energy. Yep, that's the new thing because data heat extraction becomes an issue. Okay, So that's just a digression here to talk about why we keep mentioning RISC processors and why do we want to basically let go of all the convenience of the i386 processor. The i386 architecture supports a variety of addressing modes in addition to immediate, register, direct, and indirect. But these addressing modes can be emulated by other addressing modes. We'll talk about this later, and we'll just go ahead and do some basic exposure to this. This is what we call a based addressing mode, particularly this one here. Does it resemble one addressing mode that we have seen already? Come on. Don't make me do the time loop thing.
Indirect addressing mode is what we use.
It looks almost the same as an indirect addressing mode. The indirect addressing mode is really just parentheses around a register. This is indirect addressing mode. This is what we call a based addressing mode. Well, it does something that is very similar to the indirect addressing mode. All it does is to say the location to store that 0 as a byte is the address that we store in EAX, and by the way, add 2 to it. It has an offset of 2 bytes.
So you're talking about 2 memory locations or 2 to what is being stored?
It's 2 memory locations. In this case, it's always counted in bytes. Okay, so the effective address, the actual location we are storing, is whatever EAX is plus 2.
Always increase by 2 or just
No, you can put a negative number. It will do subtraction 2. Yep.
This is used more in indirect addressing mode. Well, it is this is an indirect addressing mode.
It's kind of like a modified indirect addressing mode. The other way to look at this is, this can also be generalized in. No, I used the wrong word. This can also be specialized into the indirect addressing mode. You just put a 0 here. At 0 offset, then it becomes identical to an indirect addressing mode.
So indirect's a special case based.
Hmm?
Indirect's a special case based.
Indirect is a special case of based addressing mode. Yes. Yep.
The 2 is the space of the address, right? Like it's 2 addresses away from where
2 bytes.
2 bytes.
We're saying, don't store something at exactly where EAX points to. Store it 2 bytes away from that location. 2 bytes offset from that location. It looks kind of silly, doesn't it?
It's kind of.
But it turns out to be very handy. It turns out to be extremely handy when we get to subroutines and we want to access parameters and local variables. This turns out to be one of the most useful addressing mode of them all. Okay, so by the time we get there, we'll go back and say, oh, do you still remember what is a based addressing mode? And everybody go like, no, I don't remember. All right, so how do we test this? So once again, it is a good idea to test it again. So let's go ahead and write another test program, another simple one. So we'll call this based.s, and we'll go ahead and make a simple program, as simple as possible. L1.end, okay, feed that again. Okay. Go up again.
Do you have the hex specifier?
For feed that.
Oh, that's right. Well, let's do it like this and then see what the compiler complains. Okay, it's a very good thing that you point out the error. But remember what I was trying to do earlier. We want to actually run this through and then see what kind of error is generated. So the next time you do something like this and you see the error message, well, not knowingly do something like this and see the error message, you know potentially what is the problem. Okay. So we'll go ahead and write, a simple instruction here. We'll say, move L $L1 to EAX, basically the same thing as we did last time. And this time we'll say move B to, in parentheses, EAX to register BL. Okay, very, very similar to the one that we had earlier, just different a little bit, like that. Okay. What do you guys think? what do you think BL would be the value of BL once I fix the hexadecimal number, of course?
You won't start.
Hmm?
You won't start.
Well, first of all, let's just compile the program the way it is. I'm swapping between these two screens here. Okay. How many people think that it will complain now? Oh, that's a different thing. How come it's taking so long? Oh, I just did something very stupid. Which some of you will do eventually.
That's funny.
Okay, if you look at the command line, what am I specifying? I'm specifying AS, is the assembler. --G steps means retain the debug symbols. -O means whatever follows is the output file, right? And then I forget to specify the actual source file.
Yeah.
The assembler says it's okay. You don't have to specify the source file. I'll just take whatever is coming in through standard in, and that's what is waiting here. Okay. But the problem is, what is happening to base.s, which was my source file? It's being overwritten as we speak. So if you did something like this after spending like 2 weeks on a homework assignment, yeah, that would be bad. Another reason to use revision control.
That's a bad day.
Yeah, so right now, if I look at my files, you will actually see the damage to that file.
Yeah, exactly.
Actually, it may not be the source file that I had earlier though. Yeah, so you can see that it's all kind of jumbled up because it's the object file. I gave the assembler an empty program to assemble, and then it did all the assembling. Even though it's an empty program, it still has an output, and it overwrote my source file. But you don't see me panicking, because I still have it in the editor. Yes.
But do these numbers in the boxes mean anything?
Sorry?
Do these numbers in the boxes mean anything?
You mean these numbers?
Talking about the
Yeah, the small
Yeah,
ones.
Oh,
see the
these?
matrix right there.
They are without the scrolling. Yes. These are they're basically unprintable characters, and it's being displayed in octal. Okay, each one is basically an octal number to represent what is the value of that byte. Like this one right here. I know you guys cannot really see it. It's 0004. So it's an octal number of 4 octal. So it's the bit pattern 0000. 0100. Okay. Well, the good thing is I did not get out from my. Yeah, I want to overwrite it. Okay. Okay. This is an error message, a warning from VI itself. VI says, "Hey, somebody else is changing that file. Do you really want to overwrite it?" And the answer is yes in this case. Don't you like VI? I like VI. All right, so now we can do the same thing, except for that part. And the assembler did not complain.
Yeah, because the feed zero thinks the symbol.
It thinks it's a label.
Yeah, right.
Whenever the assembler sees a name, feed that is a valid label. Just like in a C identifier, it starts with either an underscore or an alphabet, in this case, a letter in the alphabet. And actually, assembler symbols can also start with a dot, and there are other things you can start it with. But it has, anything you can use as a C identifier, you can also use it as an assembler label. So the assembler is really lazy. When you see something like this and say, I don't know, it looks like a label to me, I'll just, stash it into my little notebook and say, that's a label here. But the label is not defined. The assembler says, it's not my job. Right? The assembler says, maybe somebody else is going to define the label. I'll just write a little note here and let the linker know about it. Yep.
Are there other special labels like start? If so, do they have an underscore as well?
You can start any label with underscore in an assembly program. Underscore start has a very specific meaning because the linker is looking for a entry point to your entire program, and that needs to be communicated to the loader of the operating system, and that's why underscore start is very, very special.
Are there others like underscore start that serve other specific needs?
You don't want to know. Yeah, there's a couple of.
Is it like BSS in all the segments and?
They're not like special labels, but like for a module underscore INIT and underscore FNIN or FINI are special labels that denote places that are called when a shared library is loaded or unloaded. There's a couple other ones, but none of them you'll use besides that.
Very good. But you cannot define those. If you define those, it will be in conflict with what the linker wants to define. So I don't think you can even define those.
Oh, underscore init you can define.
You can define that?
Those two you can define. The like start, you can define it. It's like a function. It's called when your shared library is loaded.
Okay. All right. All right. So where were we? Oh, we are trying to find out. So who is going to complain? The assembler is not complaining. The assembler says it's not my job. Somebody else is probably going to define the label. So when you run the linker, guess what the linker has to do? The linker says, I am the guy stuck with that poor job to resolve all the unresolved symbols from every file. So the linker says, this is the linker command. We only have one object file here. So the linker says, hey, somebody forget something. Okay, this label is never defined anywhere. So it's up to the linker to complain about a undefined label. The assembler says, hey, it's okay, no big deal. So let's go back and fix this one. And it will give you the same thing here. If you miss a label, if you miss the percent here, it will give you the same thing. Yeah, in this case, the assembler will not complain at all. See, the assembler says, it's fine. Because what is that addressing mode now that I forgot to put a percent symbol in front of EAX?
Label.
It becomes a label, and this particular addressing mode is called direct. It's a direct addressing mode. In other words, the assembler is saying, looking at this and go like, oh, okay, this is a direct operand. I will look at EAX as a label, and somebody's going to define that label to a certain number, and the operand, the second operand, is whatever is at that location. Not a big, no big deal. It's just a label. Somebody else is going to define it. When the linker sees this, the linker says, "Hey, it's not defined anywhere. There's a problem here." Okay. So then you have to go back here and then change that back to a percent symbol. Okay. The worst thing happens when you actually has a label called EAX. Then things get really confusing.
Then why would you use a label EAX?
I don't know. Maybe I'll give you an object file to link with all the really confusing labels defined.
Yay.
Yay.
You know what's amusing is when you tell LD to ignore it.
All right, so now the program is all fixed up. We can now go ahead and try to debug the program. But remember, before we use GDB, we want to find out exactly what it is going to do. Okay, in the first instruction, $L1 is an immediate operand. In other words, the value of the operand is exactly the expression L1 in this case. L1 is a label defined to be the address of the least significant byte of this .int, which means the AD is the one that has the address of L1. So when we move the address, which is L1 in this case, into EAX, that kind of turns EAX into a quote-unquote pointer. Okay, EAX is a register. It is not a pointer. In other words, using it as a pointer is not the only way to use EAX. There are many other ways to use EAX. It is just one way to use EAX in this case. In the second instruction, the first operand, which is the source, is specifying, oh, go to the location pointed to by EAX. Oh, wait, hold on a second here. Not exactly that location. Go past that location too. Okay, 2 locations past that one. So we are talking about this location. This is pointed to by EAX directly. This is 1 after, and now this is 2 after. So that means the first operand of the move B instruction specifies exactly that byte. So after the second instruction, the move B instruction executes, I am expecting BL to have the content of hexadecimal ED. Are we doing okay so far with the prediction of what the program is supposed to do? Doing okay so far?
Yep.
All right. So let's go ahead and give it a try and see whether that's what it's going to do. Oh, I guess I can just go back here. Assemble, link, GDB based. Okay. List the program, put a breakpoint on, well, we'll put a breakpoint on line 5. Run the program, IR EAX before the instruction. EAX has a value of 0 because it is not initialized. Single step, IR EAX again. It has the address, looks kind of familiar. Single step again. This time we want to look at BL. And BL has, whoa, negative value. Tag, you're wrong again. Why is it negative 19? I mean, but what if I do this? I get ED back. Whoa, that's just mysterious. How does ED as a hexadecimal number become negative 19? It's based on the 2's complement interpretation of values, which is not something that we have covered yet at this point. So don't worry about that part. Just use the /x to look at the bit pattern. Okay. So I'm giving you a little bit of preview, okay, of what is coming when we start to talk about 2's complement later on. Because in C it is so convenient. All you have to do is to say signed, unsigned, signed, unsigned. It's so easy. In assembly language programming, guess what? There's no such thing as signed. Everything is nothing more than bits stuck together. So we'll get to that point later on, and we'll talk about, so how does a program translate, how does your compiler generate code based on whether a variable is signed or unsigned? We'll talk about that later. But at this point, my prediction is correct, and if I look at the program again, I have just verified that the program is doing the right thing. This is what you need to do, if you have spare time, to study for this class. This will be very helpful, okay? All right, so let's go to the next slide here. Based indexed addressing mode. Well, it looks a little bit like a based addressing mode, except I have one more register inside the parentheses. What do you think this is going to do? Well, in this case, it will take a look at the value of EBX. It will add that value to the value of EDX, and then it will add 2 to the whole thing. And that whole thing, the sum of all 3 terms, become the effective address. That is where we are going to grab the source operand in this case. That's it.
Why would we want something like that?
Because it's a CISC processor, and sometimes it comes in very handy. Now this is obviously something that is way ahead of time. This comes in very handy if you define an array as a local variable, auto local variable, and it's a byte, it's a char array in C. This is very convenient because you can actually get to 1 byte in the array with 1 single operand instead of having to combine multiple instructions to get to that location of 1 byte in a char array as a auto local variable in a subroutine. Sorry? Okay. So this comes in handy sometimes, but once again, we are talking about, this is definitely a CISC type operand because it can definitely be done using smaller instructions. Okay. So, and you can also do something like this, not to specify the base register. This is called a base register, and this is called the index register. But because addition is symmetric, So you can basically flip these two, and they would still do exactly the same thing. Because all we're doing here is to add the value of edx and the value of ebx and the constant 2. The sum of these three terms becomes the effective address. It specifies the location where I will grab 4 bytes as the source operand and copy it to the destination operand, which is in this case just a register. Okay, I will leave it up to you guys to design an experiment to play with this. Okay, because it's probably a good exercise to design an experiment just to confirm that you understand the concept correctly. Now it is also possible to specify no base register and do something like this, in which case you only specify the index register, and it really serves the same purpose as a base register in this case. Yep.
One second, why is this empty before the comma?
Because I don't specify a base register. The whole point is to say that it is possible not to specify a base register. So why would we do something like this, only specify the index register, but not specify the base register? It makes no sense at all in this slide, unless you go to the next slide, in which case we have the based, scaled, indexed addressing mode. This is the holy grail of CISP instructions.
I can see like 10 slides from now. Base, scaled, indexed, address.
This is the holy grail. Every other memory addressing mode that we have talked about in this class are special cases of this one. So we just wasted an hour or so, talking about stuff that is actually special cases of the most general form of a memory operand in the i386 on the i386 architecture. So we'll take a look at this one here. We'll just look at the most general form. I don't have it here. Okay. This is an offset. It has to be a constant. It has to be a value that is resolvable by the time we link. It is nice that it's a constant like this, that it is resolvable at assemble time. But if you put a label here, it has to be resolvable by the time we link. So as long as we know what the number is before the program runs, it's all good. This is the base register. This is the index register. But in this case, we also have a number here, which is called the scale. So the effective address of this destination operand is as follows. You multiply the value of EAX by 2. You add the value of EBP to that product, and then you add -4 to that particular sum. Okay? So if I were to write this, okay, let me get rid of this. No, I'll just use a text edit for that purpose. Okay. So in the case of a based, scaled, indexed operand, the general form looks something like this. You have a certain offset, which has to be a number that is resolvable by the time the program links. You have open parentheses. You have a register that we call the base register. You have another register that we call the index register. And then you have a number that has to be 1, 2, 4, or 8 that we call the scale. The effective address has an effective address of I times S, the index register times the scale, plus the base register, plus the constant offset of n. So now that we understand the holy grail, the most general form of a memory operand, what is a direct operand? A direct operand is something like this, but without without a base register, without the index register, and without a scale. Okay. What about in the previous slide? What is a based indexed operand?
Without the scale.
Without the scale, which is implied 1. Okay.
Yeah.
If you don't specify the scale, it is implied as 1. So there you have it. Okay. That covers all the possible addressing modes of the i386 processor. Close?
One more.
There's one more?
Yeah. Segmented.
Sorry?
Segmented. You can
Segmented.
change registers.
Yeah, in this class we don't use the segment register because that is that's definitely has the x86 heritage.
The what?
That
yeah,
comes from the
x86
good old
heritage,
days
yeah.
of the
Yeah,
8086 processor. Yep. All the kludges that we try, in order to add 4 more bits to the address.
You mean segment and offset?
Hmm?
You mean segment and offset?
Mm-hmm. But there are segment registers too. Originally intended to expand the 16-bit address bus to 20-bit. But those are kludges, very, very kludgy kind of thing. All right. So are we doing okay so far with the addressing modes? Okay so far? And that's the end of this particular module. We talk about all the addressing modes. And you can probably expect the next homework assignment to have something to do with the various addressing modes here. And your job is to basically do Easter egg hunt, like the one that we're doing right now for this homework assignment.
I was thinking that all of that, the complicated thing we had, that was just the destination address, right? All the n parentheses.
No, it's just an effective address. You can use that as a source or a destination.
Also, you can use them as both.
Not both, because you cannot have 2 memory operands. You can only have up to 1 memory operands. All right, so I know we're running out of time, just in time too. I don't know where, this is just coincidental. The next module or the next topic talks about adding, and we talk about arithmetic operators, and then we talk about subtracting and comparing. That is the introduction of 2's complement. In other words, things will get confusing because we look at the same bit pattern, and sometimes we say, oh, this is a positive number. Other times we say this is a negative number. But what is it? It's both and it's neither. Okay? It depends on the context. It depends on what you're trying to do with it. The whole thing about signed versus unsigned. Now, in the C program, how do you utilize the fact that something is signed versus unsigned? Why do you want to specify it is signed or unsigned in a C program?
You get a larger number range.
You get to control the range of numbers. Okay. In other words, with a 32-bit number, you get to control whether I want to specify values from -2 billion approximately to +2 billion, or whether I want to specify from 0 to about 4 billion. That's your control. It also controls how you compare, the numbers, how you compare values, right? So in assembly language programming, the fact whether something is signed or unsigned has nothing to do with how you allocate the storage. It doesn't even have anything to do with the add instruction or the subtract instruction or the compare instructions. In other words, if you want to add 2 unsigned numbers, you use add. If you want to add 2 unsigned numbers, you use add. If you want to subtract 2 signed numbers, you use subtract. If you want to subtract 2 unsigned numbers, you use subtract. Same thing for compare. Okay? So where is that trick? Where do we say, okay, compare these numbers as signed numbers or add these numbers as unsigned numbers? Where is that trick? The trick is something that we won't get to until we get to, well, we'll talk about those when we talk about arithmetic operators, because there are status flags. Okay, there's a whole little bit. There are like 4 flags that we used in this class, and those are the ones that dictate how you look at the result of a comparison. Okay, so read those notes from topic 3, because we are moving on to topic 3. On Thursday, you will get 1 more homework assignment called MEM2, and you probably can expect what is going to be in it. It's basically another Easter egg hunt with even more restrictions. In this case, the restriction is you can only change 1 register to get the result that we want to get to. But it's basically the same principle. It's just an exercise to make sure that you understand all the addressing modes. But this is a big topic. Read ahead of me, okay? Because otherwise, things can get a little bit confusing and difficult to understand.
Okay, so we're trying to get through all of 3 this Thursday?
Well, on Thursday, we will get through at least adding, But adding is not nearly as fun as comparing and subtracting, because adding is really just stuff that we talked about already. It's basically the same as a copy instruction, except you're adding the two operands, and then you're storing the sum to the second operand. And there you go. That's basically the add instruction. It does change the 4 flags that we will talk about, but the meaning of those 4 flags after an add instruction is not particularly useful. When we talk about subtraction, which is the same thing as comparing, then things start to get interesting, because then we can say, okay, so which number is bigger after a compare? Okay, so we'll definitely get through adding. We might get through a part of subtracting on Thursday. All right, so that's it for today. I will go to the lab in case anyone needs help with their current homework assignment.